Hello friends, I'm Nikita and you are watching Prepare for GATE. In today's topic, the content of our topic is discussed in two subjects of our GATE examination, that is electronic devices plus analog electronics. Now let's look to the content. The content is, this is the syllabus for the electronic devices. The content to be discussed today will be BJT. Now BJT is a subject matter that is widely asked. A question of 1 marks or mostly 2 marks question where you need to solve the whole problem is being asked in GATE examination over previous years. So we'll take a good look into how the BJT functions. Now let's first discuss about the fundamental of bipolar junction transistor. As the name suggests, bipolar, it is 2 poles. The BJT is a basic 3-terminal device where the controls the output current. The 2 PN junction connected back to back, that is one forward biased and other reverse biased. The current, emitter current, base current and collector current are the respective regions current. The forward bias voltage is connected across the terminal emitter base and the reverse bias voltage across the terminal collector base. The 2 PN junctions form 2 depletion layers, each known as emitter junction and collector junction, where the width of the reverse bias collector junction is greater in comparison to the forward bias emitter depletion layer. The current entering through the terminal E causes electron-hole pairs generation. The majority carrier in P region and P- region is hole substitute constituting the emitter current IE and the collector current IC in the collector region. The majority carrier in base region is electrons forming base current. Now this was the basic about the PN junction. From this diagram we can see that WB is the width of the N region, P, or we can say P plus. Emitter region is always heavily doped with acceptor ions. What is acceptor ions? We have already discussed. They are the P-type ions having, no, they are not the P-type ions. They are the P-type ions means that they have 3 valence electrons in their valence shell and they can accept 1 mole electron, or that's why they have majority of holes as their charge carriers. IE is the emitter current going into the emitter region, base current going away from the base region, collector current again going away. Now you can see that the emitter and the base region depletion width is less in comparison to the base and collector, because base and collector region is reverse bias and from the formula is reverse bias, right? And we know the width is directly dependent on the biasing of the 2 junction, and emitter and base region is forward bias. That's why their depletion region is less, as the majority carrier from emitter region crosses to the base region and becomes minority charge carriers, and only minority charge carriers can be passed through this depletion region. For this region, They will be the majority charge carrier in p-type, but in n-type they will be the minority charge carriers. And being minority charge carrier in n-type, they can easily cross the depletion region. Here they have large velocity that helps them to cross this thin depletion region, and here we already know from our previous lectures that the minority carriers are unaffected by the width of the depletion region. So in this case they don't require a much energy to cross collector-based depletion region, and hence they can be partially transferred to the collector region and form this and complete their loop. So we'll next see how the currents in BJT are derived. Okay, before that, a good PNP transistor is one whose base width is less than the diffusion length. Diffusion length is actually the time is the length or the penetration when the electron crosses a region and before combining with an electron-hole pair travels in the other opposite charge carrier region. Suppose in our earlier example, when the majority charge carriers in P region, such as holes, transferred from P region to N region, then the length covered by the hole in N region before combining with an electron is termed as a diffusion length, which is equals to the diffusion constant and tau p. Tau p is the time taken by a charge carrier. Such the emitter region will diffuse to the collector diffusion without recombination in the base. This property is shown by a good PNP transistor. Thus, the majority of holes penetrating the base region are transferred to the collector region. The base current substitutes electron for the excess hole charge. However, the base region being lightly doped and narrow in width, few electron pair, hole pair recombination take place. The base current is measured in microampere. The base to emitter collector amplification alpha is equals to IE upon IB, and collector to base current amplification beta is equals to IC upon IB. Now the common relation between beta and alpha is beta is equals to alpha upon 1 minus alpha. Now here you can look at the different currents. In the diagram I have shown you that these diagrams I have taken to give you a better presentation of how actually the currents travel inside a BJT. The emitter current is crossing the emitter base region, having more number of width, larger width in N region as compared to P region, because N region is slightly doped in comparison to the P region. Similarly, in collector to base region, N region is again lightly doped in comparison to collector region. I is the whole current leaving emitter region. IC is the whole current leaving base region or entering collector region. At equilibrium, the Fermi level is flat and the band diagram corresponds to that of two back-to-back p-in junction. But for a forward bias and reverse bias collector, the Fermi level splits up into two. the excess hole concentration at the edge of the emitter depletion region becomes del PE. Okay, that is the change in the majority charge carriers, that is hole. The corresponding concentration at the end of the depletion region on the collector side of the base region becomes del PC. We can calculate del PE and del PC by this formula, where Pn is the total charge carriers in both in emitter region, exponential to the power E Q E B slash KT by Q minus 1. We can also write this as if the emitter junction is strongly forward biased, that is VEB is greater than KT by Q or VT, and strongly reverse bias, that is VEB is less than 0. Then we can reduce the earlier equations to respective equations like Pn e to the power VEB slash VT, or the change will be equals to minus Pn or minus the original current. Now, the total excess hole concentration in the base region will become IP will be equals to minus QADP diffusion constant A area Q del differentiation of dpxn o slash dxn, and the charge is 1 by 2a wbq del p. If you look at this diagram, you will clearly see how the charge carriers from one region to another region move. They have mostly considered that the minority charge carriers in each region. If you see, the minority charge carriers in P region would be the majority charge carriers of N region. The electrons, when they travel or crosses the emitter base region, they decreases with an exponential Np plus del Np and maintains at Np. When the holes from P region crosses to N region, they decreases with almost a linearity Pn plus del Pxn, and the base collector they increases to N. Okay, you can keep this diagram as your reference because most of the time quite a lot number of questions are being asked over the charge carriers. This concept is important to remember because in this you will actually see how the charge carriers crosses these junctions without considering their fields, respective electric fields. I won't say that they do not completely negate the effect of electric field. However, because of their design, they help to overcome the electric fields present within, and the charge carriers can move through the device. The Eber's Moll process. The Eber's Moll is actually one of a kind of representation of a BJT. It is again dependent on the charge carrier's representations. We can see that a normal mode representation is, I have mostly taken the section of the base region WB. 0 to WB is actually the base region or the base width, where if you see a normal mode, a forward bias normal mode, the change in concentration of emitter region charge carriers decreases over time and becomes 0 on reaching WB. The current is constant, maintaining IEN and ICN over the device. In the inverted mode, as in collector base region, or you can say about, because of the inverted mode, you can say from collector the P region charge carriers penetrates to the N region. However, the current is maintained, but the amount is less. As you compare with the earlier, the number of charge carriers is quite less. If you superimpose both the modes, in normal mode and in the inverted mode, you can say about this image that there is a decrease in charge carrier from del PE to del PC over the W base region. Looking for the symmetrical transistor, we can say that alpha IES is equal alpha N IES is equals to alpha I ICS. N is for the normal, I is for the inverted. If you know the emitter current is equals to IES del of PEN slash PN minus alpha I ICS del of PC minus PN. If you take the common out, you can say that IES over PN is del PE minus alpha N IES del PC. Similarly for base current and collector current. Have a look at these equations as they will clear your concept. In this diagram, if you represent IE in the final equations by this formula as diode and this as a current control, this as a current controlled current source, then this is a very much representation of a BJT in Eber's Moll, through Eber's Moll. Okay. Similarly, ICO, IE, you get IE and IC in inverted mode and in the normal mode. Okay. IE in the normal mode, you can represent it by two diodes and two current controlled current source, or three current controlled current source with a diode. This is ICO, reverse current, when the emitter is open circuited. Now let's look at the four different modes that we actually see when both the region are forward bias, that is a saturation region. If one is forward bias, emitter to base region is forward bias and base to collector region is reverse bias, then it's a normal mode. If both the modes are reverse bias, then it is a cutoff mode, and if the base to emitter region is reverse bias and collector to base region is forward bias, then it is an inverted mode. Now let's look current flow mechanism in NP and BJT. Till now we were discussing the internal structure, internal charge flow of the BJT, but now moving from charge carriers, we'll be discussing more about the currents and the other parameters. As we have looked into charge carrier concentration and found that N electrons almost decreases linearly in the effective base width, and these gets combined with the electron hole pair in the process. Hence they have a linear decrease as they travel across the base width region. Now let's talk about the collector current. Collector current is the current IC in the collector region when the injected electrons minus those electrons which diffuse with the neutron in NPN, the injected electrons minus those electrons that diffuse with the hole to form electron hole pairs that reaches the collector region are termed as collector current. Now, here also we can say that emitter base region is forward bias and collector base region is reverse bias. From earlier, as we have already discussed about the saturation current, the base current junction, and the collector current equation, how to get it, we have found that IC is equals to IS, reverse saturation current, e to the power VEB slash VT, where IS is the area, cross-section area, into charge, into diffusion constant, into NP0. NP0 is the charge carrier, and divided by the base width, where NP0 is equals to Ni square over Ne. They are the minority charge carriers. The saturation current doubles for every 5 degree rise in temperature. The collector current doubles for every 10 degree rise in temperature. The base current can be found by this formula. You can derive the emitter current, which is formed due to the breaking of the collector hole pairs and the dopant impurity, which release holes in the region. These both phenomena combine to form emitter current. The emitter current parameter alpha, where alpha is a common base current gain. Operation in saturation mode. In saturation mode, a BJT has VCE equals to 0.2 volts and IC is less than IC sat. These two equations helps one in determining the currents and other parameters in saturation mode. A collector base reverse current is the current flowing through the collector base region in reverse direction when the emitter is open circuit. ICBO doubles for every 10 degree rise in temperature, and ICEO is 1 plus beta ICBO. Then ICEO is greater than ICBO. Now this I want you to go through it by step, because each step, each assumption has been discussed by me earlier. When you get to know this, you will have a clear idea about what is small signal operation and what is its model, how we calculate different parameters such as beta or RE or GM, how these parameters or R pi, how these parameters are getting calculated. One should know these because this helps you to represent a BJT in a two-port networks, and R pi, GM, and beta is equals to GM into R pi. The emitter resistance RE and R pi are both equal. Also, sometimes it happens that R pi is equals to 1 plus beta RE when you have and when your emitter has a resistance attached to it. In that case, kindly look at these equations as they are most important in solving small signal analysis of your BJT. R0 comes into picture only when you have a change in modulation length and your early voltage is given VA divided by IC. Now let's look at the common emitter amplifier. common emitter amplifier. And in this diagram, the BJT is a small signal represented in a small signal manner, R pi or Rn. GM V pi is the voltage across the input resistance, and R0 is in parallel, RC is there. So V pi is Vi, the open circuit voltage gain. V0 is minus GM RC in parallel to R0. In parallel to R0, that is the output resistances, minus GM into RC. You could have RL also if a load resistance was connected to the output voltage. So you can say that AV is equals to minus alpha total resistance in collector region upon total resistance in emitter region. That is a very simple formula to remember, that the whole voltage gain V0 by Vi, I am not considering V0 by Vs, I am considering V0 by Vi or V pi is equals to minus alpha total resistance in collector region upon total resistance in emitter region, and GV is equals to minus beta total resistance in collector region upon total resistance in base region. This we are talking about common emitter. Why I have taken common emitter? Because common emitter is the most widely used amplifier. Now, earlier I told you about Re, R pi could be equals to 1 plus beta Re. This is the scenario where it actually happens. The amplifier input resistance Rin is given. Then Rn is equals to 1 plus beta Re plus Re. Re 1 plus beta Re. One is with included Re and other is without Re. With AV0 is equals to V0 by Vi minus G to RC in parallel with R0 minus GM into RC upon 1 plus GM into R. With emitter resistance it becomes this. And as we already discussed, AV is minus alpha into total resistance at collector region upon total resistance at emitter region. I think I have forgotten about putting this equation here too. Okay, so it becomes like this. Now it's perfect. Then AV, GV. Look at these equations carefully, remember them well, because you will be asked. It has happened many times that an emitter is common emitter amplifier with emitter resistance has come, or simply a common emitter amplifier has come. Now, one needs to calculate by himself how to get the value. Okay, AV0 is minus GM into RC in parallel with R0, 1 plus GM into R0. Simply it could be minus GM into RC divided by 1 plus GM into RE. As this RE is degrading the whole gain, that's why it is called emitter degeneration resistance. The input resistance is increased by this factor 1 plus GM into RE. The voltage gain is reduced by this factor 1 plus GM into Re. The overall voltage gain is less dependent on the value of beta. And that's a good point, because beta is a quantity which changes with temperature. And if that changes with temperature, then it is sensitive to the change in temperature, which will affect our normal working of our device. And for not having to reduce that effect, we attach a resistor at the emitter, and with the decrease in gain, but we make the whole circuit gain beta free. Okay. Now the biasing in BJT amplifier circuit. Again, I would like you to go through these why I'm saying again and again, because see, the diagrams, I'm lucky enough that I got such a self-explanatory diagrams. With basic knowledge of networks, you can apply Kirchhoff's law, voltage divider, to get these equations that have been mentioned. These equations, this is on division. I use VEE minus VBE RB RE plus RB slash beta plus 1. Okay. Rather than just remembering all these equations, what will be more a benefit for you is to get the holistic idea how it's been done. If you remember the logic behind, you can apply these equations at the time of solving actual questions. Okay. The practical BJT looks like this. They have capacitors connected across them. Now let's look one of the 2017 year gate question. So as you can see in this, that an emitter is connected. That's why it will be a beta free, right? First of all, and we have been given VT, VBE. R0 is practically infinite. That means it will not be affecting our calculations. Under this equation, we need to find midband voltage gain AB V0 by VI. Okay, let's look at the calculation. If this is our DC analysis graph, for DC analysis having common emitter RE, I think I should mention it with capital R. That is more appropriate. And AV is equals to RC. Okay, if you see for the DC analysis, what we have open circuited all the capacitors. If you open circuit all the capacitors, you can calculate VB at this point, which is VCC R2 upon R2 by R1. You can calculate VE at this point. Once you calculate VE and divide by RE, you can get IE. Now here the all analysis, DC analysis is over. Now if you consider the AC analysis or the effect of capacitor at this point of time, what you will do is short circuit all the capacitors. Short circuit all the capacitors. If you short circuit all capacitors and the DC is grounded, okay, DC is grounded and you have short circuited all the capacitor, that means the RC will be across the load, and with RL, as you can see that in the question there is an RL2, that means RC and RL will become parallel to each other. Okay, and your RE parameter in that case will be equals to VT divided by IE. IE we have already derived, we got RE. We have RC and RL values, and if you put them in your equation, you get RC divided by RL, not divided by RC in parallel with RL divided by IE, and you get your voltage gain, and this is independent of any beta value. Okay, now that's all for this today's lecture tutorials. Hope you like it. At this point I would suggest you to go through BJT more carefully, because most of the time this mid-band gain voltages, mid-band gain are often asked, and that's why I suggest you to do the questions or them more, practice more. Thank you.